Okay, so in this video I'm going to go through the June 2011 Unit 1 paper. So let's start off with some particle physics. So we've got name two baryons to kick us off, so nice and easy. So we're going to go with the two most common. So the two most common are the nucleons, so we're going to go with protons and neutrons as the baryons. Next question, state the quark structure of a pion. So a pion is not strange, so there'll be no strange quarks, and it needs a positive charge. So to get a positive charge, you need an up to give you 2/3, and then you're going to need an anti-down to give you the remaining third there. And you know it can't be a strange quark or an anti-strange in this case because it's not a chaos. The K plus particle is a strange particle. Give one characteristic of a strange particle that makes it different from a particle that is not strange. This seems very obvious, but is that it contains a strange quark. You don't need to have anything more complicated than that. This is just a chance for you to demonstrate that strangeness comes from having strange quarks. And you could also have gone with other things like having a longer than expected half-life, because that's what's the effect of strange quarks, or maybe it decays by weak interaction, but this one's the main one really. One of the following equations represents a possible decay of a K plus particle. State which one of these decays is not possible. So let's have a look. So with the first one, let's check charge. Goes +1 to +1, seems fine. Bottom one charge +1 to +1, that's fine. So if we look at baryon number, there's no baryons anywhere. If we look at lepton number, aha. So in terms of lepton number, the top one is 0 to 0. The bottom one, a mu plus, is an antiparticle, so that's -1 and that's -1. So you've got a no conservation of the muon lepton number. So the second So we've got muon lepton number is not conserved. And what's happening is it's going from nothing to -2 there, because we've got two anti-leptons. Okay, so let's move on to the next one. Another strange particle X decays in the following way. State which interaction is involved in this decay. So we can see that afterwards we've got two particles which are not strange, because there's a pion and a proton, but we started with a strange one, so it's got to be weak interaction. It can't be strong, because strangeness has to be conserved in the strong interaction. So those are the two things that can cause decay: strong interaction, weak interaction, but it can't be strong because strangeness isn't conserved, leaving you with weak. Show that X must be a neutral particle. So if we look at the equation in terms of charge, so we've got it going to -1 plus +1 equals 0. So the charge after is 0, so the charge before must also be 0 to ensure charge is conserved. Okay, so we've got one last part to have a look. Okay, so deduce whether X is a meson, baryon, or lepton, explaining how you arrived at your answer. So let's just rewrite the equation so we know what we're looking at. So we've got X going to pi minus and a proton. So first thing we can deduce is we've got a baryon number of +1 on the side, so this must be a baryon. So it must be either a proton or a neutron, but we're not asked to deduce that here. We just need to know what type it is. So ion number is +1, therefore X must be a baryon. To conserve baryon number, which is something that is always conserved in all interactions. Okay, so which particle in this interaction is the most stable? Well, we know it's not the thing on the left, otherwise it wouldn't be decaying, so that can't be right. So we're comparing a proton and a pi minus, and a proton is the most stable type of hadron, so we're going to go with a proton being the most stable, because all baryons try and decay into a proton, so you know it's really stable, and pi, like mesons, a quark and antiquark, is not a stable state. Alright, so that concludes particle physics. Let's move on to the next question. Okay, so we've got alpha decay is a process by which an unstable isotope may decay. State what is meant by isotopes. So this is like the second year in a row this question's come up, so you should be familiar with this one. So it's so they're atoms of the same element. So the two key features you want for this, with the same proton number, so that's first mark, so we've got the same proton number but a different number of neutrons. Number of neutrons. And that gives you, blimey, that doesn't look like different. Anyway, a different number of neutrons. So those are your two marks, same number of protons, different number of neutrons. It wants to complete an equation for alpha decay. So the nucleon number must have decreased by 4, A minus 4. The proton number must have decreased by 2. So that gives you essentially this equation. Calculate the specific charge of an alpha particle. Specific charge is charge divided by mass. So the charge has got 2 protons, so it's 2 times 1.60 times 10 to the minus 19. That's the charge divided by 4 times 1.67 times 10 to the minus 27. That's the mass of an alpha particle. Once we do that calculation, we end up with 4.8 times 10 to the 7 coulombs per kilogram. There, because it's charge divided by mass. So that shouldn't be too surprising as the unit. Okay, so let's finish off. So it wants us to explain why the alpha particle, once outside the nucleus, is unaffected by the strong force. So one of the key features you should know about the strong force is its range. So strong force has a range of 3 to 5 femtometers. That's a key property you should know about the strong force. So essentially so once it's outside of the nucleus, then it's going to be out of the range of the strong force. So that's what we can see there. Got the strong force's range. When it's outside the nucleus, the alpha particle is outside this range, which is why it's unaffected. Okay, so that completes this question on subatomic particles. Let's move on to the next. Continuing with the theme of particle physics, we've got an isotope of potassium, and it can decay by positron emission, so beta plus emission, to form an isotope of argon. Okay, so we know it's going to produce argon, and we know it's going to produce a positron which can be represented like this. So it also must be producing an electron neutrino to conserve electron lepton number. So this one must be 18. Nucleon number doesn't change during beta plus decay, so you should end up with 4018 argon, and if you happen to know your periodic table, you would know that was right as well. And then we've got those 2 part leptons produced as well to conserve electron lepton number. The following equation represents another possible decay. So what we can see here is electron capture, because we can see we've got weak interaction causing decay forming this happen here. So this is electron capture. So what's happening in this reaction is that the nucleus of the krypton is a proton in it is interacting with an inner shell electron by the weak interaction, forming a neutron and producing electron neutrino to conserve electron lepton number. So in terms of where it comes from the inner shell of where the electrons are. Okay. Explain why this reaction has to produce a neutrino rather than anti-neutrino. Well, it's to conserve electron lepton number. Alrighty, so then let's finish off this. Okay, so to finish off, it wants us to complete a Feynman diagram showing this decay. So we've got a proton turning into a neutron there, and we've got an electron neutrino being produced as part of the leptons. So we've got a positive charge being carried from left to right, so we've got a W plus boson going from left to right. Theoretically, you could also have drawn it a W minus going to the left, but conventionally you show it going from baryons to leptons, which is why you can see what I've done there. Okay, so that finishes this question. Let's move on to the next one about electron energy levels. So we've got this paper's longer answer question. So line spectra reserved before they could be explained by theory. We now know that photons of a characteristic frequency are emitted when the vapor of an element is bombarded by energetic electrons. The spectrum of the light contains lines of a definite wavelength. Explain how the bombarding electrons cause atoms of the vapor to emit photons. The existence of a spectrum consisting of lines of a definite frequency supports the view that atoms have discrete energy levels. So let's address this first part to start with. So this part here, why the electrons cause it. So what happens is, let's call them incident electrons. So that's the ones that are coming in. And what they're going to do, they're going to collide with orbital electrons and transfer them their kinetic energy. Okay, so let's review what I've got here. So the incident electrons, the ones coming in, collide with orbital electrons, the one sitting in whatever atom we're doing, and the incident electrons transfer their kinetic energy to move the orbital electrons to a higher energy level, and that's called an excited state. So state. Okay, so that's why it's the process, and then to finish that off in terms of explaining why that causes photons to be emitted. So this state is unstable. So to get more stable, the electron de-excites to a lower energy level, and that's why it emits a photon. So that's the first part of the question there. So let's tick that off. We've done that one. Then it wants to know why a spectrum of specific lines supports the view that atoms have discrete energy levels. So photon energy is calculated by E equals HF. So if the photons have certain wavelength or frequency, that means they have specific energy as well. So that's what we've got there. Using the equation E equals HF, we've got photons of a certain frequency or wavelength. That means they have a specific energy in the photons. Okay, so what that means is that the energy gaps in the atoms, the changes in energy, must be fixed. So that evidence is there being fixed energy levels. So let's finish that off. So that's the final part we've got here. So because we get photons of a certain energy, that means electrons can only be making certain energy transitions, which is where the energy comes from in the atom, which gives the idea of the electrons can only take fixed energy levels with certain values there. So that's that question right there. So let's move on to the next. Okay, so to finish off the energy level stuff, I'm going to look at a few things. So we've got ionization of a hydrogen atom is 13.6 electron volts. What's meant by ionization energy? So this is the energy required to move an electron from ground state to an ionized state, so remove it completely from the atom. So that's what we've got there, the definition of ionization energy, to go from ground state to completely outside the atom. Express the ionization energy of hydrogen in joules, giving your answer to an appropriate number of significant figures. So we've got 13.6 electron volts, so we're going to multiply that by 1 electron volt, which is this value, and that's going to come out as 2.18 times 10 to the minus 18 joules. So fairly straightforward conversion there that you all should know how to make. Alright, so that concludes the energy level stuff. Alright, so this question looks at AC circuitry. So if you've currently only studied DC, do feel free to skip past this question. You might not meet this until year 13 on the new specification. But let's crack on through it anyway. So we've got a screen when we've got a 1.5 volt cell connected to the Y input. So we can see that 1.5 is 3 squares, or there's 0.5 volts per division is the Y gain there. Okay. On the grid below, show the appearance of the screen if the Y input is now connected to 2.5. So that's going to be 5 squares. So it's going to be a blob that I'm not doing very well with this pen right here, because it's going to be 5 squares to be 2.5. Okay, so let's move on. The Y input is now connected to a sinusoidal AC voltage supply, and we've got this screen shown. So it's just going up and down, which would indicate the time base is currently switched off. Explain why a vertical line is now seen on the screen. So the voltage So the voltage oscillates between positive and negative, which is why it goes up and down. And time base is switched off, which is why it's a vertical line. Vertical motion. So if the time base is switched on, that's what means it goes across the screen. If the time base is switched off, that's what gives you a vertical line. Okay, so if we look at this diagram, we can actually see that this is oscillating between plus 2 volts and minus 2 volts. We're probably going to need that, so let's go on. So it wants the peak-to-peak voltage of the AC supply, so that's going to be 4 volts between the 2 peaks. And then it wants the root mean square voltage, so But first of all, we need the peak, which is 2 volts. So the RMS is 2 over root 2, which is about like 1.4 something to 2 significant figures. So that gives you RMS. So moving on to look at some DC stuff. So we've got a cell of EMF that's given. We've got internal resistance of R, and we're connected to a variable resistor R. So this is essentially the internal resistance experiment. The current through the cell and terminal potential difference are measured as R is decreased. So if you decrease the external resistance, current's going to increase, and that's going to change the terminal PD. Okay, so let's get to the actual question. Now we've got a graph of the results of this experiment. So this graph is of the form minus Ri plus EMF. You should be familiar with that, having done the experiment as part of the course. So you can see the gradient is minus 1 times the internal resistance. The y-intercept is the EMF. So if we look at that, that's 1.44, 1.48. So that's the EMF is about 1.52 according to this graph. So let's first of all look at what we're asked. So explain why terminal PD decreases as current increases. Okay, so the first thing is if we look at the equation, let's just do it in its conventional form for now because it's IR. So you can see from this equation, internal resistance and EMF stay the same, current increases, so a bigger value is subtracted from it, or there's a greater potential difference across the internal resistance there. So let's go with that one. So there's a greater potential difference across internal resistance, EMF is constant because it is for any power source, they have a fixed EMF. So therefore, so V must decrease. And if we think about that practically, if we increase the current, what we must have done is decrease the external resistance there. We're going to use the graph to find the EMF, so that's the y-intercept, which is going to be, as I said earlier, 1.52 there. And I'm guessing on the next page it's going to ask us to work out what the gradient is. So let's do that now. So I'm going to use the 152 and 0 as 1 point. Let's use this one over here. So 0.40, 2.50. So I've done it the opposite way around, the like normal change way and change in x, but it doesn't matter really. Minus 0.40 divided by 2.50 gives us minus 0.448, which is roughly minus 0.45. There is your gradient. So you can see that the internal resistance is going to be about 0.45. So let's move on and see if. So you can see I was exactly right. The next question is about internal resistance. So you just times your gradient by -1, get 0.45 ohms there. So you'd need to show what you were doing. So showing you were calculating the gradient, getting it right, times it by -1. That's where the 3 marks come from. So it wants us to draw a line on the graph that shows the results obtained from a cell with the same EMF but double the internal resistance. So I'm just going to write what you would draw. So you should have same y-intercept there, and you should have double the gradient, if that's correct. gradient on your graph. I can't show you because my program is not sophisticated enough to show you that. Sorry about that. Same EMF, but negligible internal resistance. So what we're going to have here is we're going to have the same intercept again because it's got the same EMF. But it's going to be a horizontal line. Because the potential difference across the external resistors is just going to be equal to the EMF the whole time because it's the only component in the circuit. So the potential difference won't change because it's no longer a potential divider. Okay, so in the original circuit shown, the variable resistor is set at a value such that the current through the cell is 0.89. Calculate the charge flowing through the cell in 15 seconds. So we're using Q equals IT, which is 0.89 times 15. So that gives us 13 coulombs there. That's your charge. The final part of the question is calculate the energy dissipated in the internal resistance. So we're going to be using P equals I squared R. So you've got the value of current. We calculated the value of the internal resistance. So put those together, it's going to give us 0.36 watts. Okay, so let's move on to the final question 7. So we've got a circuit with some resistors W, X, Y, and Z, and we've got no internal resistance this time. EMF is 10 volts, and the ammeter reading is 2 amps. Get the total resistance. So total resistance is going to be the EMF divided by the current, which is 10 over 2, which is 5 ohms. There, going around. All right, so let's move on to the next. So we've got the resistors W, X, Y, and Z all have the same resistance. Show that your answer to the previous part is consistent with the resistance of each resistor being 3 ohms. So let's have a look at how this works. So we've got the parallel ones. So we know that total resistance is 5 ohms. So in the system we had let's work out what the resistance of the parallel section is. So one pathway was 1 resistance, one pathway was 1 over 2R. So that gives us the resistance of the parallel section. If we add those two together, we get 2 over 2R plus is 3 over 2R, so is 2R over 3. So the total resistance is just going to be adding an R to that. So adding 3 over 3R, which is 5R over 3, which we know is equal to 5. So multiply the 3 across, gives you 5R is equal to 15, gives you R equals 3 ohms there if we do that. Okay. Now we need to work out through the current through resistor Y. So we know the total current going around is 2 amps. So that's going to split up 2/3 one way, 1/3 the other way. So Y is by itself. So it's essentially going to be 2/3 times by 2, which is 4 over 3, which is 1.3 amps there. So if you think about it, you've got double the resistance one way, so it's going to have 1/3, and then you've got half the resistance the other way, so you're going to get 2/3 of the current. That's how I work that out. We're going to 1.3. Then it wants us to work out the potential difference across resistor W. So we know the current through it is going to be 2 minus that, so is 0.67 amps. Then you know the PD is IR it's 0.67 times by 3, and that's going to be 2 volts. I'm just going to round off this paper. So if there's anything that's not been clear as they've gone through, please do let me know in the comments on this video. I hope you found that useful. Please do make use of other materials like this that I've made, and thank you very much for watching.